Hello and thank you for watching. In this video we're going to go through some limit laws. We're going to state them and we're going to prove them. So far we've only been proving limits, but we slowly want to build up our artillery to actually solve our limits, to actually find those limits. So far we've just been given some results and we've been assuming them to be true and then proving them, but we want to start being able to find those ourselves. So our first step is to prove some laws that we can use with limits. The laws we're going to go through in this video is if we have some limit as x goes to a of f of x, or kf of x, or no, if we have this, then we also have that the limit as x goes to a of k times f of x, this is equal to kl. This is one law that we're going to prove in this video. And the second law is if we have that as the limit as x goes to a of f of x equals l, and the limit as x goes to a of g of x equals m, then we have that the limit as x goes to a of f of x plus g of x equals l plus m. Okay, let's start with proving this first. So essentially, since we have a positive epsilon in our definition, we can still continue. This is just an arbitrary epsilon, so we can just continue by saying, okay, so if we have some f of x minus l being less than epsilon, then we can also say that, okay, we can choose our epsilon to be over this modulus of k, and we want it to be the modulus because we want it to be positive. Otherwise, if we had a negative k, then this is no longer greater than 0, and we want epsilon greater than 0. So suppose we have this, so then we want to show that if we have x minus a being less than delta, we want to show that this goes to this. However, notice that if we have this, then we just have that if we multiply through, we have that the modulus of k times f of x minus l is less than epsilon, which means that we have k f of x minus k of l being less than epsilon. And okay, well, this is just our redefined limit. This is just this, and this kl, this is just this. So we're basically already where we want it to be. So for this, let's just see what this says. So if we choose some delta, well, no, sorry, if we choose some epsilon, then this will imply this. However, since this is also implied, then we have that if we choose some delta to be equal to delta 1, then we have that we have the limit as x goes to a, so when absolute value of x minus a is less than delta 1, we have that k times f of x minus kl is less than epsilon, and that's all we really need to do in this case. So therefore we have that. So therefore we have this thing we had above here. Okay, now for the second law, this is what we're trying to show here. So okay, by definition we have that if we have the limit as x goes to a of f of x equal to l, then we also have some absolute value of x minus a being less than delta 1, and we also have, and by this we also have some absolute value of of x minus a less than delta 2. And also we have that f of x minus L is less than some epsilon, and we have that some g of x minus L is less than epsilon. We'll say this is epsilon 1 and this is epsilon 2. Or yeah, actually no, we'll just say they're both less than epsilon because we arbitrarily define our epsilon. We just choose any epsilon value you want. So now if we add those together, just the right hand sides, then we get that f of x minus L plus g of x minus L is less than 2 epsilon. Oh, 2 epsilon. We just added this together, we can do this. So actually, when we look at this, we think maybe it would be better if we just define this epsilon to be epsilon over 2 instead, just so we can get rid of this 2 here. And so we'll get this, which is useful. And okay, we have this. And if we think about it, we have the triangle inequality, which means that we have f of x minus L plus, oh sorry, this was supposed to be an m, g of x minus m is less than or equal to this expression here. So we have x minus f of x minus L plus g of x minus m, which is less than epsilon. So this is even smaller than this for any given epsilon. So we can still say that we have f of x plus g of x minus L minus m, so minus L plus m being less than epsilon. Okay, we added those together, so we have to do something about this now. We want to go from our step over here to our step over here. We've already done most of the work, because this is saying that if we have some limit to something, we don't know what we're going to if we ignore this, of f of x plus g of x being equal to L plus m. This is just like the final part of what we need. So essentially, if we have this, if we have this being less than delta 1 and this being less than delta 2, and then if we take the minimum value of the two, then we have that less than minimum of delta 1 and delta 2. And the reason why we do this is because, okay, if we take the smaller value of the two, then clearly both this and this will be smaller than the minimum, or equal to, I guess. Because let's say delta 1 is smaller than delta 2, then clearly we can still write that, we can clearly just write that x minus a is still less than delta 2, of course, because delta 1 is smaller. So if it's less than delta 1, then it's going to be less than delta 2 if we take them, if delta 1 is smaller. So we can do this. So if we choose our if we choose our delta to be the minimum of the two, so choose delta to be min of delta 1, delta 2, and then we'll just get this, we get that f of x plus, or minus L plus the modulus of g of x minus m is less than epsilon. I guess we skipped a step because we did not write our epsilon over 2s or anything of the sort, but the principle still holds, and so we get that by the triangle inequality, we get that f of x plus g of x minus L plus m is less than epsilon. And so this is basically saying, okay, we have our given epsilon, and so if this holds, then we have that the limit as x goes to a, because we have a here, of f of x plus g of x equals this thing here, so we have L plus m. And so I'm basically saying that if we add two functions in a limit, we can just add their respective limits. That's all for this video. Thanks for watching. Bye bye.